Okay, good morning, good afternoon. The subject of today is to how to finally prove the fundamental theorem by constructing an expansion. But before that, so no homework is assigned this week. That was scheduled in advance. We need some time off. But homework 6 is due. But if you want, we can start with a little discussion of homework 6 and then postpone the due date perhaps to Friday. Will this be useful for anybody?
Yeah, I was going to ask the question.
Yes.
Homework 6 at some point.
Okay, good. So in that case, let's do that. So homework 6 is no longer due today, it is due on Friday. If I forget, somebody should email me. Please email me a reminder. Okay, somebody right now. Okay, because otherwise I'll forget and then it will be a mess. Because CrowdMark will think, anyway. So there are two things I wanted to say. One is, theta is the multiplication operator by the one chord diagram theta. That's obvious, right? So multiplication by theta, so uppercase theta will be the map. So uppercase theta will be the map that will map the chord diagram anything to add another chord to it. Isolated, so it will be of course it doesn't matter where you add it, so long as it does not intersect anything else. So maybe it will be that. That's clear. D theta. So this is the tough one. Let d theta be the adjoint. Nope, that was a mistake. I thought I was using the right, where is the highlighter? Oh, here is the highlighter. I pressed the wrong thing. So d theta is the adjoint of multiplication by w theta, where w theta is the obvious dual of theta. That's very convoluted. But at the end, it's something very, 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 very simple. So, what is w theta? So, w theta is the adjoint of, the dual of theta. So, w theta should satisfy that w theta of theta is equal to 1, and w theta of anything else should be 0, but now in degrees or any other basis element should be 0. In degree 1 there is only one element, so really that's the only condition. So really what remains is to say is that w theta of anything of any other degree, so anything not of degree 1 should be 0. And sorry about that, I just realized that in my preparations today I forgot to shut down a background program that's running and it's taking CPU power, and since it's taking CPU power I have lag. Okay, so now what is the adjoint of multiplication by w theta? Oh my God, the adjoint, God, do I know what this is? The adjoint of multiplication by w theta. So if I have a diagram D, then d theta, so this is the adjoint of, this is what I called the adjoint of multiplication by theta. So d theta was w theta adjoint. So you know, maybe I should remind everybody, including myself, what is the adjoint of a linear transformation. So if you have t going from one vector space to another, then its adjoint, T dual, is going from W dual into V dual, and it has the property, it is defined by the property that if you have a vector u here and a vector z in V dual, or so you know what, since it's in W dual, maybe I will call it omega, so Greeks for the dual. So if you have a vector omega in W dual and a vector u in V, then Tu, that's in W, so it can be evaluated on W, on omega, so omega of Tu should be equal to T dual of omega evaluated on, so T dual of omega is in V dual evaluated on U. That's the definition of the adjoint, right? So now d theta should be the adjoint of multiplication by W theta star. So d theta of d, when you evaluate it on against any linear functional, so against any phi where phi belongs to a dual, should be equal to multiplication by theta, so W theta times phi when evaluated on D. Right? This is the defining property. This is how d theta should be defined. It should satisfy this for every phi. Now, multiplication of linear functionals is defined using the coproduct. So this should be W theta tensor phi computed on the coproduct of D, right? And where the coproduct of D is in A tensor A, so this lives in A tensor A, and you have two linear functionals on A, so you have these two linear functionals, you evaluate one on the first component, the second on the second component, and then multiply the results. Okay? Now, what does this mean in practice? The coproduct is defined by, so if you have a diagram D, the coproduct is the sum of all ways of splitting it. One component, some of the chords go to the left and some of the chords go to the right. But then we evaluate the left factor against W theta. W theta is 1 if and only if it is fed with a single chord. W theta is 1 if and only if it is fed with a single chord. So this becomes the sum of all ways of splitting D into one chord goes here, which means and then you get 1, and the rest remain to be evaluated with phi. So this is really equal to phi evaluated on all diagrams obtained from maybe I was too optimistic about how much space I need. So all diagrams obtained from D by dropping one chord. So we found that phi of d theta of d is equal to phi of something else. And this should be true for every phi. But this just means that d theta of d is equal to that. So the conclusion is that d theta of d is equal to whatever is written here inside a parenthesis. So sum of all ways of dropping one chord from D. Okay? So for example, suppose we start from the chord diagram written here, then d theta will map it to a sum of three terms, each obtained by dropping one of the chords from here. So if you drop the left chord, you're left with an X. If you drop the backslash, you're left with this. And if you drop the slash, you're left with that. So in fact, these two are the same, so they get added, but you know, that's fine. Okay, so now we understand what's d theta. Wait, d theta is also, now, okay, now we also should understand the name. I mean, what does differentiation, how does differentiation act? So, oh, I ran out of space, I'm sorry. I need another page, so append page, good. So, how does differentiation act? What is the derivative with respect to x of some polynomial? I don't know, x to the 7. Well, it's really, well, you write x to the 7, so here is x to the 7. You know, maybe I should have stopped at 5. So you write x to the 5, and differentiation with respect to x is the sum of all ways of dropping one of these x's. So it's the sum of all ways of dropping one of the x's. Since all the x's are the same, you get, in each case, you get x to the 4th, but you get it 5 times because there were 5 x's that you could have dropped, so you get 5x to the 4th. And actually, when you prove how differentiation works, I mean, this is exactly how the proof ends up working. Okay? So the analogy is clear. Theta was the diagram with one chord, and d theta is all the ways of dropping one chord. The analogy should be clear. The analogy is even stronger. So differentiation has the property that the commutator of differentiation with respect to x and multiplication with respect to x is equal to the identity. And in fact, if you've taken quantum mechanics, this is the absolute basics of quantum mechanics. This is the so-called Heisenberg commutation relation. And all of quantum mechanics is somehow founded on this. Okay? It should not be surprising that we get the same relation. The commutation with respect, the commutation of differentiation with respect to theta and multiplication by theta should be the identity. And in fact, this is the first thing that you were asked to prove. oops. Sorry, I have to wait. Okay, this is the first thing that you had to prove. Now I do want to make one further comment. So there is this equality, okay? So, or not this equality, this definition. We are defining a map P from A to A by this funny formula. Where did it come from? Okay? So, first of all, what is it supposed to do? So P is supposed to be the Hopf algebra morphism from A reduced to A. So it should be the map from A modulo the ideal generated by theta, this is A reduced, into A. Okay? But how would you define, if you had a, I mean, how would you, if it really was a polynomial ring, how would you define a map from, say, Q of X and Y into, modulo the ideal generated by X? What? Oh no, I erased the wrong thing. Sorry, modulo the ideal generated by X into Q of X and Y. The answer, the best way to do it is to evaluate at X equals to 0. Right? If you want to get from a polynomial of X and Y, but in such a way that X will go to 0, well, you evaluate at X equals to 0. Now, what is okay, so I want to somehow write evaluation at X equals to 0 using the tools that I have. The tools that I have are differentiation and multiplication. Okay? And fortunately, there is a way to do it. Namely, if I had a function f and I wanted to evaluate it at x equals to 0, I would write f goes to f of x minus x. Well, that's the same as evaluating it at 0. And then I'd use the Taylor series where this is like the A and this is the delta A. Okay? So this will be the sum as n goes from 0 to infinity of delta A to the power n divided by n factorial, so minus x to the power n divided by n factorial, multiplying the nth derivative with respect to x of the function f. But if you look at it, this is exactly the formula written here. Okay? So, so everything here is to justify the Taylor formula for, well, in our context, or a piece of the Taylor formula in our context. And it ends up being a useful result because it constructs a map from A reduced to A, which again, I remind you, since Lie algebra gives us functional on A, so since Lie algebra gives us functional on A, we thus get functionals on A reduced. Okay? Sorry, questions, comments, or did I overload you?
Yeah,
you probably wanted simple, you probably had simple questions, and instead of giving you simple answers, I gave you deep philosophy.
Yes, I have two comments. So one was, so at first when I saw adjoint, I got confused. So when you read the map, so it meaning we can use adjoint and, is it pullback? Yeah, pullback interchangeably.
Yeah, adjoint is the same as pulling back linear functionals, yes.
I see. And the second is, so with this kind of differentiation, we can generalize to say differentiating chord diagrams with, n chord diagrams instead of maybe just a single chord diagram, right?
Yeah, no, I mean, then you extend linearly. I explained how d theta acts on a single chord diagram, but if you have a linear combination, well, it's a linear map, so you act on each one the same way. Okay? Good. Sorry, so...
I actually had a question about problem 2 on the homework.
Oh, what was problem 2?
Problem 2 is about, it's the four-color theorem.
Let me see if I can put it on the screen. Okay? Oh, this one. Right, yeah.
Yeah.
Okay, yes. Yeah.
Okay, yeah. So prove that WGLN of D is a polynomial in degree n of degree at most being over 2 plus 2, and that the coefficient of this top term is non-zero if and only if it can be embedded in the plane without solid intersections.
Yeah.
I've been able to prove one part of that. I've been able to prove that if the n to the v over 2 plus 2 term is non-zero, then it can be embedded. But I seem to have found counterexamples to the other direction. For instance, if you take the so-called like dumbbell diagram, where you have two circles and a line between them.
Let me. I really hope you're wrong. The dumbbell diagram.
I mean, I have the counterexample, and then I have what I think is a fix to the counterexample. But
let's compute WGLN
of
the dumbbell diagram, right?
Yeah.
Now we expect it to be, so V here is equal to 2. So
yeah.
So V over 2 plus 2 is 3. So we expect to get
n cubed.
n cubed times a coefficient which better be non-zero.
Yeah.
Right?
But
yeah.
The problem is, no matter how, so you look at all possible ways of evaluating
Yes.
the trivalent versus.
Yeah, no, you are right. Yeah.
And every way you evaluate it, you end up with 3 loops. And
Right.
so you get 4 n cubed terms, and they all cancel.
Yes.
Because you get opposite sides.
You are right.
And in fact, if you have any sort of, if you just isolate the like 1/2 of the dumbbell, it will always, you always get 2 evaluations of that, which differ by a sign but have the same number of loops.
Yeah.
And also, this diagram we know has to evaluate to 0 because of anti-symmetry.
You are absolutely right, and it seems that I wrote something slightly wrong. What is your fix?
Well, I mean, my fix was that it's not really a counterexample because the number of vertices in a diagram isn't really defined modulo STU relations, or AS in this case.
No.
So the problem...
No. These are vacuum diagrams. There are no STU relations. There is no skeleton. There are only IHX relations.
But also AS, right?
Antisymmetry and AS, and antisymmetry and IHX. But these relations preserve the number of vertices.
For instance, that diagram evaluates to 0 modulo AS. Because if you evaluate one of the ends of the
you are right. This diagram,
AS, you still get the same thing, just with a
no,
little twist.
no, you are right, and indeed I think you found a counterexample to what I wrote. But the fix is not to say that V is not well defined.
Okay.
Now, what is the fix?
I mean, the other way would be that when you look at the sum, because the only, if the diagram D is embeddable in the plane without self-intersections if and only if, when you compute this algorithm, you get n to the v over 2 plus 2 terms in it. They might cancel each other out in this case, but you'll get them in the summation. That seems to be one.
No. I actually, I actually, okay, you caught me. We're in the middle of a class. It's not a good time to resolve it. The resolution will be. I'm slightly confused. Maybe I wanted to say. So, you know what I want to stand behind is the equivalence with the four-color theorem. Okay? The complement of this diagram is actually not a map because it has a country that borders itself. Right?
Okay.
It is possible that I was too quick. I mean, let me go back home and reformulate it in a way that will eliminate this diagram. Okay?
Okay, thanks.
And so send me now you owe me another, not owe me, but please send me another email.
Okay.
Okay? Oi. Okay, anyway, unfortunately we don't have enough time now for the what I really wanted to say today. So I'll start and let's see how far we go. Okay? So remember, in order to prove the fundamental theorem, every weight system integrates to an invariant, which in particular means that there are invariants for each Lie algebra and each representation. So to prove this, we need an expansion or a universal finite type invariant, which is a map Z from the space of knots to the space of core diagrams with the properties that if you evaluate Z on a singular knot, I didn't especially indicate that K is singular because it could be non-singular as well, right? If K has no singularities, this still makes sense. In any rate, you get the diagram of K plus higher order terms. For a non-singular knot, the diagram would simply be an empty circle with no chords. Okay? And I know several proofs of this theorem, and none of them are easy. None of them is easy. All of them are hard. All of them require either analysis or very difficult algebra. So I want to give you just a taste of the prettiest of the proofs. Okay? But you'll see that it's pretty, but it's also, well, it will be clear that in order to fill in all the details, you'll need a lot of work. Okay? So here is the proof, or here is the beginning of the proof. So first of all, let's start from some philosophy. So, the word Stonehenge is mentioned here. So, Stonehenge has all sort of cosmic coincidence properties. Okay? So, if you stand in the big stone on the left and you look towards the big stone on the right, then exactly on the shortest day of the year, the sun appears just at the corner or something like that, okay? So what I want to do is to count cosmic coincidences that involve a knot, okay? So, suppose you have a knot in R3, and for the purpose of today, the knot becomes a specific embedding. Okay? Later I will have to show you how the result changes when I change the embedding, but I start with a specific rigid embedding in R3. Also, I'm assuming that there is a large number of stars picked in advance in heavens. So, you know, the North Star, the sun at the midday of the shortest day of the year, Sirius, and I don't know, a few others. Okay, so you know, to turn it into mathematics, I really mean that you fixed a number of generic points in S2, right? Heavens, right, is just S2. Okay, and when I say generic, I mean points so that there are no coincidences, no three are collinear, everything is, they're random. Okay, and then an example of a cosmic coincidence would be if you are able to find 3 points on the knot. I hope the picture is clear enough. Okay, so 3 points on the knot such that the lines from these 3 points into and towards the three of the stars that you've chosen. So in our case, it's a purple star, a green star, and a blue star. Then all 3 lines pass through a single point. Okay? So let's figure out how likely is it that you will find such cosmic coincidences. Okay? Basically, I need to count equations and unknowns and see if the number of equations is equal to the number of unknowns, then it's likely that I will be able to find finitely many such cosmic coincidences, right? If there are more equations and unknowns, then likely there will be no cosmic coincidences. And if there are more unknowns and equations, then it will not make sense to count the solutions because there will be infinitely many solutions. Okay? So let's see. What are the unknowns here? So the unknowns live here. So the unknowns in this picture, oh, I misspelled unknowns. So the unknowns in this picture live in, so the point where the purple line meets the knot, the point where the green line meets the knot, and the points where the blue line meets the knot. So the unknowns live in S1 cross S1 cross S1. And then there is a further unknown point, which is the point, the black point, the point where those 3 lines meet. So that's a point in R3, and in general, the number of unknowns here, so the number of unknowns here is 6, right? The dimension of the space of unknowns is 6. Okay? Now, what are the equations? So the equations are, the blue line is pointing at a star. A star is a point in a 2-dimensional space. So I basically have to compute the direction of the blue line and then declare that it should be equal to the position of the blue star. That's 2 equations. 2, right? Because the blue star is a point in heavens and heavens is S2. Okay? So you have one equation for the blue star, and you know, if I really want to be fancy, then there are also an S2 sort of worth of equations for the green star and another S2 for the purple star. But I'll stop being fancy because it will take too much time. But again, this is a 6-dimensional space, so you can expect that if you have a generic knot, so if this was placed in a random way in R3, and if the 3 stars were chosen randomly, then the number of solutions, namely the number of ways of placing pens on the knot in such a way, actually it's a purple pen, so pens on the knot in the way such that their tips will point at stars will be finite. So I want you to count this number and call it the Stonehenge pairing of the diagram D with the knot K, where D is the diagram drawn here and the knot K is, well, your fixed knot. Now, I want you to count with signs. So how do you count with signs? You know, this is a bit of a little bit of an art, okay? But you know, there is some justice in saying that when you count the solutions of the quadratic, one comes with a plus and one comes with a minus. Somehow, in one place you're increasing, in another place you're decreasing. Okay? But the same thing makes sense in general. Namely, really what we have here is a map going from the space of unknowns to the space of equations. The map is, so if you have a point in S1 cross S1 cross S1 cross R3, so if you have a specific point where you've specified all 4 points that I've now indicated, then that specifies the 3 directions. That specifies the 3 directions. So you get a map from this space to that space. And really what I'm counting is, well, I pick a specific point in this space, namely a point in heavens for the purple line, a point in heavens for the green line, and a point in heaven for the blue line. And then what I'm counting is the number of inverse images of that point, right? But whenever you have a map between 2 manifolds, so whenever you have a map F between 2 manifolds, if you have a point in the target manifold, it makes sense to count, if the 2 manifolds are of the same dimension, it makes sense to count the inverse images with signs, namely near every solution, so near every x which maps to n, you check if locally the map preserves the orientation or reverses the orientation, and that determines the sign. Okay? So I don't think, well, you know, if I wanted to put all the details, it will take a long time. So, and I told you I don't want to do it, okay? So I'm just saying that this Stonehenge pairing of this diagram with a knot should be defined, and it's a number it's an integer which could be positive or negative because I'm counting with signs. Okay? Now, the same pairing, the same Stonehenge pairing is in fact makes sense for other diagrams. So in fact I could compute the Stonehenge pairing equally well of, say, this diagram with any knot. Why? Because in fact, let me, well, I still have to do some dimension count. I have to check that the number of equations is equal to the number of unknowns. So, so let's calculate the number of equations and the number of unknowns for the diagram written here. So let's see. First of all, we have 1, 2, 3, 4, 5, 6 points on the circle. So we have dimension 1 for each point on the circle, and these are unknowns. We also have 2 points in R3, so each one, right? So when I mean by a cosmic coincidence corresponding to this diagram will be, so a point in R3 for each internal vertex, and a placement of the external vertices on the knot in such a way that all the lines are pointing at stars, including this inner line. Okay, so anyway, these are 3 unknowns. These are also 3 unknowns. So the number of unknowns in total is, what is it, 12. Okay, now what is the number of equations? So you have 2 equations for each line, because each line must be pointing at a star. So you have 2 plus 2 plus 2 plus 2 plus 2 plus 2. These are 6 2's, and the sum of 6 2's is also 12. And in fact, for every diagram of the diagrams that make the space A, the number of equations will be equal to the number of unknowns. Yes, Leonard?
So for the middle line, is it not pointing to 2 stars?
Oh, it should be, no. The 2 points, the stars are not the black points. The black points are points in R3. I want the lines to point at stars. So these 2 points are points in R3, they are not stars. But the line between them should be pointing at in R3. So you know, if I were to draw this diagram, or if I want to draw a configuration that matches this diagram, it would look something like that. So I would have the knot, I would have sort of a 3D construct like this on top of it, and the 3D construct will have the property that each line, when continued, is pointing at a star. Not the same star, so I mean, and this line also, when continued, should be pointing at a star. Is this okay?
In the reverse direction, it also points at a star, right? But so we count it once, right?
Yeah. Okay. Good.
Right, does that mean we pick an orientation for that line or something?
So,
to choose whether we extend it?
So, count it into the signs that I'm not going to discuss. But the answer is yes. For all of this to make sense, you have to pick orientations, and then you have to show that the orientations at the very end don't matter, and there's a lot of work. Okay? And I'm only sketching it. Okay? So I claim that for every diagram, for every trivalent diagram, the number of equations will be equal to the number of unknowns. And in fact, it's completely trivial. The only thing you need to know is the equality 1 plus 1 is equal to 2. Because what you do is, instead of writing these 2, instead of writing all of these 2's as the number 2, you write them as 1 and 1, 1 and 1, 1 and 1. So you write 1 near each end of each edge, and that's the same as writing 2 on each edge. But then this one cancels this one cancels this one, and so on. And the 3's cancel 3 1s each, so you always get equality. Okay? So, yeah, so this makes sense for every trivalent graph. Maybe I'll give you the simplest example. So the simplest example is in fact the case of links. So the core diagrams, instead of being a single circle with chords, they will be a pair of circles with chords in between them. And let me count the pairing of this chord diagram, which has 2 circles and a chord in between, with some specific link. Well, I need to choose a star. The star I will choose will be vertical up. Or differently, or said differently, if I'm looking at the diagram from above, the star will be my eye. So the chopsticks, well, I mean, when I gave this talk the first time, I was using chopstick, but the pens that are supposed to point from at a star, in this case should be vertical. So really I'm counting the number of places where one component passes under another, so that the line in between them will be vertical. And that count is the count of the number of crossings. And when you count the number of crossings between 2 components, you get the linking number. So the linking number is an example of an invariant which is computed by cosmic coincidences, except the cosmic, the star is your eye, so you tend not to see it. Okay? Anyway, I would have said a lot more about it, but the next thing to do is to compute the generating function of all cosmic coincidences. And let me make this picture a bit bigger. I'm sorry about this. Right. So this is an idea of Dylan Thurston. So here's a picture of Dylan Thurston. And what I want to do is to compute all cosmic coincidences at once. So I'll make a generating function out of them. So first of all, I'll take the limit as n goes to infinity. N is the number of stars. I basically want to have many, many, many stars so that the counting will make sense even for very, very complicated diagrams. But on the other hand, I will divide by n choose e, where e is the number of edges in a diagram. So I'll basically renormalize it so that if you increase the number of stars, the end result, these 2 things should cancel. Okay? And then I'm looking at the sum over all possible diagrams. For each diagram, I will take its Stonehenge pairing with the knot k and multiply it by the diagram D itself. So then I get an element in A. Okay? And ignore this. This we can talk about later. Okay? So this defines a map from knots to the space A. Okay? And the claim is that modulo signs, of course I didn't tell you anything about sign conventions, orientation convention, all that, but I'm claiming that once we put all the signs in order, and once we explain this framing dependent counter term, this will be what you wanted. This will be the universal finite type invariant. Okay? And this will have to wait to next time, but I'll have to explain to you next time why the IHX relation is necessary. So I'm actually not going to assert that this is an invariant. So I'm not going to assert that this Stonehenge pairing in itself produces a numerical invariant. I'm only going to assert that if you pack all of them together and mod out by the IHX relation and the STU relation and the anti-symmetry relation, so only then you get an invariant. So I have to explain where in this crazy description the IHX relation comes from. And the IHX relation end up coming from this crazy diagram drawn here, but I'm afraid well, I'll have to explain it next time. So see you on Friday. Any questions, any comments?
So in the sum above, we are taking sums over all possible trivalent graphs, right?
Basically all the graphs that make up A. So not quite trivalent graphs, right? These are trivalent graphs with a skeleton. So a circle and inside it a trivalent graph. Exactly the diagrams that make up A. Each such diagram corresponds to a cosmic coincidence. So I find an expression in A in which I sum over all diagram. For each diagram, the coefficient will be the number of cosmic coincidences of that diagram on our knot. That's the invariant.
So are you saying that this will eventually be zero, the sum, to make sense of this nicely?
Sorry, say it again. Am I saying that?
So can we expect this sum to be eventually zero to make sense of this nicely?
No,
Because
it's
right
not.
now
No, it's not going to be zero. This is the universal finite type invariant.
I meant the terms of the terms in the sum eventually being zero. Is that something we expect?
No, what's going to happen is that when I've defined this sum, but it depends on many things, right? So it depends on a choice of a specific embedding of the knot. What if I deform the knot a little bit? It depends on the choice of the stars. What if I move the stars a little bit? The claim is that if you deform the knot or move the stars, this sum will change, but it will only change by IHX and STU relations and AS. So basically, once you mod out by the relations, the sum becomes invariant. So in fact, you could have guessed these relations, IHX and STU, without knowing anything about finite type invariants. You could have guessed them by counting cosmic coincidences. I mean, that's not how history went, but it could have gone that way. Oh, I'm lying to you. In a sense, that's how history went. In a sense, this predates finite type invariance. This is somehow a direct consequence of Chern-Simons theory. So in a sense, it predates finite type invariance by about a year or two. Not by a lot. Okay, but I'll have to continue the discussion next time. Any other questions or comments?
This is a bit of a pointless question, but how did you typeset the Stonehenge?
This?
Yeah.
I have my own font. So I have I have my own DBN font. No, DBN Simb. So if you Google DBN Simb, Simb, I think that's how it's called, you'll find that I have a font that contains all the crazy symbols that only I need. And that's one of the symbols in that font, I think. Okay? Possibly this predates the font. I hope not. I hope I'm not lying to you. Okay, so see you on Friday, and again, I owe you a very, very complicated picture that explains how the IHX relations arise. But it's actually very natural also once you think about it. Okay, so see you on Friday.